The objective of this topic is to know the procedure used to perform an impact test, and then understand the test results.
The basic purpose of the impact test is to determine the behavior of a material once it has been struck by a sudden blow. The test provides data for measuring the toughness of a material at various temperatures. The toughness of a material is extremely important when designing pressure vessels, bridges, ships, and other structures. The weldment must be able to resist the formation and growth of cracks within its operating temperatures. Through impact testing, base and filler metals are evaluated to determine their ability to provide toughness.
The most common form of impact test is the Charpy V-notch, so called because the specimen is prepared with a precisely machined notch. Specimens are removed from the test piece transverse to the axis of the weld, that is, across the weld. Usually a series of specimens is removed, the number depending on the applicable quality specification. Normally 5, 7, or more are required to properly determine impact properties.
The dimensions of the specimens are important to the accuracy of the test. Exact dimensions are obtained by machining, based on the quality specification and the testing procedure.
The three common types of specimens used with the Charpy test include the V-notch, the keyhole notch, and the U-notch. The V-notch is the most common. The notch is precisely machined to ensure the reliability of the results.
Once the required number of specimens has been machined to procedure specifications, they are stamped for identification. Both ends should be stamped so that broken halves can be matched and evaluated.
The test is begun by cooling the specimens. Methanol and liquid nitrogen are sometimes used in a refrigerated bath for this purpose. The impact strength of a material is determined by measuring the energy absorbed in the fracture in terms of foot-pounds. The Charpy impact machine provides the impact force with a free-falling pendulum, which can produce as much as 300 foot-pounds of energy. The amount of energy depends on the weight of the pendulum and the distance it travels to apply the load.
The test specimen is placed in the support fixture against the anvil at the base of the machine. It is supported at both ends and positioned so that the notch is centered on the side opposite the pendulum strike. The pendulum is then released from a fixed standard height and allowed to swing downward. As it falls, it builds up energy, and at the bottom of the swing is capable of delivering 300 foot-pounds of energy.
Notice that at this point a measurement gauge has been activated. Here's how the gauge works. The gauge starts at 300 foot-pounds. If the pendulum is released without a specimen in the fixture, the gauge indicates 0. However, if the pendulum is released with a specimen in the fixture, the specimen absorbs some of the 300 foot-pounds of force and prevents the pendulum from making a full swing. The gauge needle registers the amount of absorbed energy, and the foot-pounds are recorded.
Some quality specifications may require a series of specimens to be cooled to minus 20 degrees Fahrenheit at the time they are broken. This is a typical test for certification of carbon steel filler metals. The material meets the necessary toughness requirements if all specimens are capable of sustaining the minimum acceptable foot-pounds of energy.
An alternate procedure consists of preparing a series of specimens to be tested at various temperatures. Groups of 5 or more specimens may be tested at each temperature. The results are then averaged to obtain a foot-pound value at each temperature. The results can be plotted on an energy transition curve. The curve developed for carbon steel shows an upper and lower shelf. The lower shelf indicates that the material has lost toughness in this temperature range, while the upper shelf indicates good toughness properties. At lower temperatures, steels normally become more brittle and lose toughness.
A measure of ductility is also possible. This is the degree of lateral expansion of the fracture surface, sometimes called the Mills lateral expansion. More expansion of the side adjacent to the notch after testing is an indication that the material has greater ductility. The fractured surfaces can also be evaluated as ductile or brittle. Some standards require that 50% or more of the surface must appear ductile.
The Charpy Impact Test is commonly used to certify filler metals and qualify welding procedures. The procedure for conducting the test, the number and type of specimens, and standards of acceptability may be specified by the American Welding Society, the American Society for Testing and Materials, the American Society of Mechanical Engineers, military specifications, or others. Other types of tests used to measure toughness properties include the drop weight test, the crack tip opening displacement test, and the explosion bulge test. Although not as common as the Charpy test, they may be specified by some quality specifications.